forward present you the simulation of the effect of nature-based solutions as a mitigation tool for urban heat islands specifically. So the overview of the presentation is going to go through the contextualization. I'm going to give you a very brief framework of the necessary concepts, land surface temperature and land cover dynamics, then how to model the urban heat island susceptibility, and the model to model the surface urban heat island intensity as a hazard. And afterwards, I will explain you which are the nature-based solutions that are simulated to mitigate such hazards. So starting from the contextualization, I will go through the urban heat island phenomenon, the machine learning approaches, and the Harmonia project, like a very brief overview, because this was the starting point of this research. So as you all know, the urban heat island effect is a phenomenon that occurs in the city centers mainly, where the urban areas, or any area in particular, has a higher temperature than the reference temperature provided by the vegetated and forested areas. So the urban heat island susceptibility in this context can be defined as the likelihood of the urban heat island effect happening at a specific location. Some nature-based solutions have been proposed to mitigate the effects of these hazards, and these include enhancing the urban greenery, albedo, green roofs, and so on. I will go at the end of this presentation to show you how these possible simulations can fit in an urban heat island scenario. So going through the machine learning approaches for the susceptibility modeling and the mapping of environmental hazards. So I created not only for the urban heat island, but let's say for pollution, flooding, and any environmental hazard, susceptibility mapping, this general framework. That starts from grabbing data from multiple sources, such as sensor data, satellite and remote sense data, and authoritative data sets, like any of the data sets that we all use from ARPA Lombardia or from Regione Lombardia. Then all this data splits into the historical occurrences and the conditioning factors. So if we put it into a modeling approach, the historical occurrences are going to be our target variable, while the conditioning factors are the independent ones. The conditioning factors, depending on the hazard, are going to go through socioeconomic, topographic, land cover, or meteorological factors. Afterwards, there's going to be a data pre-processing step that has to happen in any research, basically. And in this case, we have to, as we are working mainly with spatial data, we have to put it into the same spatial resolution, gap fills, remove outliers, and so on. Afterwards, depending on the number of conditioning factors that we have, we may carry out a feature selection to remove highly correlated variables that will introduce too much variability to our model. And afterwards, we can go to the machine and deep learning approaches. In here, it happens as well, I'm not sure if you have worked a lot with machine learning, but inside any model, it's not just defining the different parameters. We should go through like a research on its own to select the number of features and set up, for example, if we are working with neural networks, define the number of neurons, and if we're working with tree-based models, define the number of trees, and so on. Afterwards, we perform the accuracy assessment. This machine learning modeling can happen among multiple models, and therefore we must try them out to get what is the best model. And afterwards, we can produce our susceptibility maps that can be interpreted, used for other purposes, such as the simulation of the nature-based solutions in this case. and some spatial agreements and external validation data. So this research was published with Professor Rovelli as a literature review on machine and deep learning for susceptibility mapping. Focused particularly on the air pollution, flooding, urban heat islands, and landslides. The main findings of this research were the spatial agreement of susceptibility maps. Multiple studies show which are the modeling results, and the maps basically look different. So there must be a point in which they have to converge, and all of them having high accuracies, the spatial representation is different. The utilization of explainable AI to interpret the model and results, and the analysis and correlation of land cover and land use and uncovered landscape patterns. I will go through one of these in this presentation. So the brief overview on the Harmonia project, EU Horizon 2020, we participated in a task as DICA into effectively the susceptibility modeling. So the pilot cities for the project were the cities of Milan, Sofia, Ixelles, and Piraeus. And the model hazards were air pollution, urban heat island, and flood only in the city of Milan, because unfortunately there was no data to train for this hazard in the other cities. So the project has already been delivered a while ago, and the literature review was one of the outputs of this project. And just to show you example of the work that was carried out, the urban heat island, actually the surface urban heat island was modeled for the pilot cities, and here you have the maps. Okay, so I will go now through the land surface temperature and land cover dynamics. Today I will focus on the city of Milan for the study, and I will go through the DUSAF Landsat 8 imagery, the trends among these two, and the MSPA, the morphological spatial pattern analysis, that is one of these landscape pattern analysis I was mentioning previously. So here we have the city of Milan, the comune and the metropolitan city, because the comune is too small and the urban heat island effect is basically happening everywhere. So to have a bit more of a spatial variability to train our model, we consider a larger area of interest. So land cover, DUSAF generalization. DUSAF is the land cover dataset provided by Regione Lombardia every 3 years. Just to clarify, the previous maps that I showed for the surface urban heat island susceptibility were produced using the Urban Atlas. But Urban Atlas has a lower frequency in which they release this map. So I decided to move to DUSAF to have a bit more of precision on the land cover, even if we will see the land cover changes throughout the years of the study are not so significant, but still to pursue more accuracy, then I decided to move to DUSAF. Just that the number of classes in DUSAF are too many, and I decided to map them as general classes into residential, industrial, transportation, urban green areas, agricultural, forest, and water bodies and wetlands. Just one thing to mention in here is that they have into urban green areas, they have 2 subclasses. One were like parks, and the other were sport facilities. I decided to move the sport facilities into the second class, which is industrial, abandoned areas, and anything else that doesn't fit into other classes, because sport facilities included like stadiums and also like many soccer fields, which are mainly covered by plastic grass. So this was actually not having the same behavior as grass. So the Landsat 8 imagery was used for land surface temperature. So in this case, I systematically downloaded the data from 2015 to 2022. And This data was already downloaded at the level 2 C2, so I really needed to use the additive and multiplicative factors to derive the land surface temperature in kelvins, and just to showcase here, there are the examples of the years of 2015, 2018, 2020, and 2022. For the, sorry, this is not surface urban heat island intensity, this is land surface temperature, and it is ranging from 280 to 340 Kelvin. So, yeah, you can see that it varies a lot. Also, these maps, just to further clarify on the data, I downloaded multiple scenes during the summer only, but at the end I made a mosaic of each year during summer to smooth a bit the signal because I was having too much variability, and I wanted to provide a general summer scenario. You will see later on the results. So in the same way, having the land surface temperature and the different land cover classes, the urban heat island, in this case, the surface urban heat island, can be defined as the, with the reference temperature, that is the temperature on vegetated and forest classes, and then the surface urban heat island are going to be binary maps, having 1 if they are surpassing this reference threshold, or 0 if not. On the other hand, the intensity, that is what you're seeing here in the maps, is going to represent the difference between the reference temperature and the temperature in each of the pixels. Okay, so here I just provided a summary, a small summary of the land cover and land surface temperature trends. So here you see like how much the variability is. It's very small. Like in the DUSAF, I used the 3 available years in the time range that were 2015, 2018, and 2021. And the changes are very small, but that's quite normal in the cities. So there are some cities that have these huge urbanizations, and it's not the case in here. There are some small changes that we can see in the matrix up here. I just made a very brief summary of what's going on. So there are like residential going to industrial, transportation, and urban green areas. And in the same way, industrial is small, slightly going into other classes, and then transportation going through urban areas, and agricultural to forest and urban green. But most of them are only into the degree of a few kilometers, not even arriving to 2 square kilometers in the change of the area. But these small changes gives us an understanding that there is an ongoing interplay between the urban expansion, environmental preservation, and land resource management due to the very small changes that are happening. And then in the graph down here, you can see the summary that I made for each of the DUSAF classes with respect to the land surface temperature. So we can see from the first, like, sorry, the font is quite small. Our residential, industrial, and transportation infrastructure are the first 3 dots in the lines, and these correspond to the, of course, the highest temperatures ranging from 315 to 320 kelvins. Then we have the natural areas ranging from 309 to 315, which are the last 3, and we have then the urban green areas in the middle, ranging from 314 to 318 Kelvin. Okay, sorry. Okay. So now I present you the morphological spatial pattern analysis. This is just a characterization of the landscape geometries and connectivity proposed by Swall. I think it's French. in 2009, and it has been applied into multiple fields, like to verify deforestation patterns, and even in medicine, because you can interpret any sort of pattern that you can see in the images. So I decided to apply it to the vegetation pattern. So I produced a binary map or a mask of the locations or of the vegetation areas, and provided it to the program, where they have this computation, and this is the result. And the result per each one of the land cover years. So mainly we have core classes. So there are multiple classes for this MSPA, and the core and the edge are the ones that are more present in the area of interest, while the rest are very non-significant, I would say. We will see then how these MSPA classes are related with the surface orogeny intensity. So now, arriving into the methodology, the surface orogeny intensity susceptibility. So as I was mentioning from the initial diagram, there is, of course, the data and the data processing step that goes into a machine learning model to provide, to produce the susceptibility map. So in this case, the data were all these Landsat 8 derived indexes, like the NDVI, albedo, the land surface temperature, just in the case of the susceptibility, and the land cover. There was, I used other ancillary data like population density and building height. So the training consisted into taking my 7 mosaic summer images of Landsat 8 and sampling 10,000 points from each of them. So I would have at the end approximately 7,000 points. There are going to be some null values here and there. And the sampling of these 10,000 points was stratified, so I divided it equally into 4 setups, having a change into vegetated and urban heat island present, and toggling this into the different 4 cases. The overall accuracy was 87%, and of course, as expected, the most important parameter according to the random forest importance specification was the land surface temperature, afterwards the NDVI, population density, and then agricultural areas and urban green areas of the land cover classes. So this is the result of the surface urban heat island susceptibility. It just gives us a characterization. So it's the likelihood of a surface urban heat island happening in that specific location in terms of percentage. It's a very general characterization of the surface urban heat island phenomenon. And we can see that for sure where there are the concentrated built-up areas, the surface urban heat island is quite high. Also in the north, where there are more towns. So now moving to the surface urban heat island intensity as a hazard. So in this case, I used the same diagram, just like land surface temperature was not considered because I didn't want to model the surface urban heat island intensity in terms of what is the land surface temperature that we are expecting. Because as you saw, if you recall the surface urban heat island intensity maps, this varies throughout the year. So if I expect to give a temperature difference with respect to what I'm expecting, what the temperature that I'm expecting in a specific year, it's going to vary a lot, even inside a same season. So I decided to independently model the intensity of the surface urban heat island based on the NDVI, albedo, and the ancillary data, excluding the land surface temperature. So the setup was mostly the same. So I had the same 10,000 points. I still had some information on the urban heat island to make the sampling. Then I didn't provide it to the model. And at the end, I obtained a mean absolute error of 2.65 Kelvin. It's not super precise because, as I tell you, with this variability, there are several peaks in both sides, so negative and positive peaks in the intensity, which sometimes are also related to errors because if there are even small clouds and if you are filtering even in the surrounding, there may be some errors, and the temperature, the land surface temperature, is highly distorted from this information. So this is the result of the surface orbohedral intensity, and instead of providing just a characterization in this case, we have a data that is varying spatially, and in this case it is ranging. This is ranging from minus 10 to 10, so having in yellow the areas that are having the reference temperature, and we can see that Milan, even in the center, is having the highest surface orbohedral intensity. And then if we produce the zonal statistics of the surface orbohedral intensity with respect to the MSPA classes, we can understand that the core perforations loops are having the highest intensity temperatures, while the background that are mostly all the other classes that are not vegetation are having the highest peaks on the surface orbohedral intensity. So these models the base of these models was, as I told you, produced during this Harmonia project. Then I decided to extend it into the intensity, but I wanted to find another purpose of the model, just to, instead of just producing the map and showing here, I made a characterization or just a map of the intensity of the surface orbohedral. I wanted to play with the parameters of the model to understand how these simulated changes could produce any sort of insight on where I could place different nature-based solutions. As per nature-based solutions, we are talking about the introduction of green areas in multiple forms. It could be parks, grasslands, green roofs, and so on. So I'm going to show you two cases. The first is simulating green roofs, and here we have what we have here. Do you know what this is? Yeah. So we are right here. I found a layer of the neighborhoods of Milan, and because I started sampling, I said, okay, if I want to put some green roofs, which would be the most, let's say, smart way to place them? So I started just randomly taking some polygons here or there from the DUSAF residential areas, but considering the MSPA, we see that, of course, core patterns are giving us a higher cooling effect. So I took a neighborhood, I put it on top, I sampled the dense residential areas in here, and I masked them out with the buildings, because even if the DUSAF is quite precise, still in a whole like house or building, we can take backyards, we can take some streets. So to be very precise, I masked this with the building height to exclude anything that was with the zero building height. So to take into consideration only the built-up areas. This resulted, so just the roofs, resulted in a cover area of 0.7 square kilometers, which is something considerable. That seeing all the numbers of the land cover changes and so on. So we are not talking about huge numbers. It's not that we can change like tens of squares of kilometers. It's a huge change. So this is already a huge change. The bounding box that contains this raster is of 5.6 kilometers. And yeah, I just told you this information already, so let's go to the next slide. Okay. So for making the simulation, I made a sampling of the urban green areas inside the city and took their average NDVI, albedo, and so on. So to simulate that I was having vegetation in there. And these were the numbers respectively, which I checked. I don't have the information right here, but I did check with multiple studies, and this is I wouldn't say standard, but it was good that I could get similar numbers from the city averages. So this is the result. So then I made a correlation, or just I extracted the statistics between the original surface urban heat island intensity map and the green roofs in the areas where I was placing the green roofs, not even outside. And these are the statistics. So there was a 5 Kelvin decrease in the mean temperature, and the max temperature diminished from around 13 to 5 Kelvin. So this is, of course, not for sure that I can say I'm going to place the green roofs and this is going to be exactly the output. But it's just to, if this gives us some information about how the surface urban heat island is changing with respect to simulated nature-based solutions, then it's going to be it should be somehow proportional to what we could find in the reality in case any of this implementation happens. So it's a tool for pre-analyzing possible implementation of nature-based solution scenarios. So a second one that I made was not green roof, sorry, was the green corridors. So thinking that the MSPA and the core vegetation areas are providing the higher cooling effects, I decided to increase this area a bit. So I put a buffer of 5 meters around the core vegetation areas, and also bridges connecting the vegetation areas that were nearby. Nearby meaning with a distance less or equal than the buffer size, so 5 meters. And the selected buffer size was 5 meters, and the area was 4.6 square kilometers. This is quite a lot, considering that I'm surrounding all the vegetation areas in the city. Here, I don't know if you can appreciate much, but here are some of the green corridors and the bridges. So these were the results. The results is that there was a decrease of around 1K, but we must consider that these were already one of the classes that were having the lowest surface urban heat island intensity, because we had the urban vegetation. So it decreased a bit, it improved the scenario, and so this is also another possible solution. Of course, I put a surrounding in all of the vegetation areas. There are places where we have mainly transportation infrastructure and so on, and it's not quite feasible that we can implement all these. But even with this, we can have like a proportional idea of what could be the temperature decrease regarding the surface temperature. So to conclude, the surface urban heat island susceptibility and intensity maps based on the land surface temperature are able to explain the overall behavior of and the spatial distribution of the surface urban heat island. The produced model with the surface urban heat island intensity serves as a basis for evaluating the effect of possible land cover changes regarding the mitigation of the surface urban heat island. Like I just presented 2 setups, but depending on the scenarios, we could simulate anything that we want. It's just to provide a mask or where you want to place the new areas. Green roofs, as you saw, and green corridors provided a decrease on the intensity of the surface Orvekid Island, and is consistent also with the results of similar studies. Finally, the potential reproducibility of the model in other areas is quite easy. You saw that it was done in the beginning, using urban atlas or other local land cover maps. Just that keeping in mind that I have seen this many times in reading a lot of susceptibility papers, the studies tend to be not time consistent, so very like considering only one layer at in time. So the more time variability we introduce to the model, the more significant are going to be our results with respect to the reality. So yeah, that's it. Thank you very much.
Any questions for